Alrighty, now we're going to start on the second section of the trust analysis. I want you guys to follow along. Please pause and rewind. This is going to be a lot of math, and I don't want anybody lost. So if you suddenly get lost, rewind it and rewatch. Please expect to take probably twice as long. Rewatching this probably at least once again, so that you're not lost. So we're going to be doing what is called the analysis of trust by methods of joints. And the way we do that is we disassemble the truss down into its points. We then do free body diagrams at every single joint. Now, each joints, what we're going to do is we have the forces exerted on members. They are going to always be, the forces are always going to be assumed to go in line with the beams. So they are going to be going in or pulling out. They never go in a diagonal direction. And the force on this one is going to be the same on this pin. And also it's going to be the same down here. So they're always equal and opposites if they're pulling apart or compressing. Now we can use the three equilibrium equations from the previous video to solve for the entire truss. Now, I want to emphasize this. If the forces are negative, that means the force is under compression. So that means that the forces are going to be inward here. And if they're positive, they're going to be outward. Now, we're going to always assume that they're always being pulled apart unless the numbers come out as a negative number. So let's start with a sample problem. This is a truss. Now we have to first determine, is it statically determinate? To do that, we need to label all the reactionary forces. So the reactionary forces are the forces that are going to be on our pins and rollers. So rollers only have one reactionary force, and that's always in the upward direction. The pins have two, one up and one lateral. So the roller only prevents it from going down into the floor. It can freely move left and right. But the pin allows it to, is going to lock it in the left-right direction and the up-down direction. So now we have to determine using the statically determinate equation to see if it is actually statically determinate. So how many joints do we have? We have 1, 2, 3, 4, 5. So that's going to be 2 times 5. And then we have members 1, 2, 3, 4, 5, 6, 7. 7 members, and we have the 3 reactionary forces. So 2 times 5 is 10, and 7 plus 3 is also 10. This is statically determinate. If any of these numbers do not equal the same number, then you cannot do this upcoming steps. It is impossible to do. So using the method of joints, you would determine the forces in each member of the truss. So what we're going to do is, based on the free body diagrams of the entire truss, we're going to solve using the 3 equilibrium equations for the reactionary forces. So we're looking for the reactionary forces at points E and C. And then we can then break it down. After that, we're going to use point A, is the only one we have the least number of unknowns. So we have only an unknown here and here. Now, our goal is, again, to find what is the force at every single beam. Some of these beams are going to be large and take up a large load, and some of them are going to be smaller loads, and they can even have 0 loads. And we need to know that. So how big is my piece of steel need to be, or is it could be like aluminum, or it could be dental floss, or just a cable? If it's under tension, it could be legitimately a cable. It doesn't need to be a full steel member, which would make it cheaper and easier. So the way we do this is we're going to then come through and we're going to successfully look at every single point, and we're going to start with A, then we're going to move to D, and then B, and then E, and then finally C, to get them all out. So once we get to C, however, we'll have already learned everything else. So C, we don't even have to do. So technically, we're going to only have to do 4 free body diagrams. C, because we'll know B and E, and B and E's are going to be identical. This, whatever BC, this member is going to be the same as B as C on B. And EC is the same as CE. So we're going to find those forces, and then at point C, you could just basically check it to see if the results are correct. So now, Based on the free body diagram of the entire truss, what we're going to do is we're going to solve the 3 equilibrium equations. Now, I'm not going to go clicking through all this. I'm going to leave all the math, and I will go down with the mouse, kind of just driving down the math. So follow it. I don't want to click it, and so that you can look through the math and find what's going on. All right. So the first thing I'm going to do is we're going to look at the moments, and we're going to pin it at point C. Why? Well, because it's the pivot. That's where we are pinned, and it's allowed to rotate around that pin. It makes sense. It's easier. You could actually imaginarily pin it at point A and see what happens, and it would work just the same. But we're just going to do it at point C because it's easier that way. So we have our 10 kilonewton force, and it's multiplied by its distance away from the pivot point at 12 meters. Then we have our 5 kilonewton force and its distance of 6 kilonewtons. Then we have our reactionary force, which we don't know at point E, and it is pushing at a distance of 3. So what we can do is we can plug it in. 10 times 12 is 120. Plus 5 times 6 is going to be 30. Now notice these are positive numbers because these are causing it to go in the counterclockwise direction. The E is trying to make it go in the clockwise direction. So that's going to be a negative number. So then where you plug it in, 120 plus 30 is equal minus X times 3 is all equal to 0. We rearrange that equation, we solve it, and it comes out as 50 kilonewtons in the positive direction because it would be a negative number. And that is going to make it go in the clockwise direction, 50 kilonewtons. Now we're going to find the reactionary forces at point C. Point C has no other x's. There is no other left-right direction. So the sum of all the forces in the x direction have to be 0. And since there's only one force in the x direction, it has to be 0. So the reactionary force at point C in the x direction is 0. Now in the y direction, though, the y direction, we have the forces in the y. We're going to add them all up. So we have a negative 10 kilonewtons because it's going down, plus a negative 5 going down, plus this E, which we already found out. The reactionary force was the 50 kilonewtons up. So that's a positive, plus this CY. We don't know what that number is. We're going to find that one. So we take negative 10 plus negative 5 plus 50, and that comes out as a negative 35 kilonewtons. And so that's our down direction. So that negative denotes that this is actually an arrow should be flipped. That's actually pushing down. So all the force downward is actually being supported by the roller here. And in fact, even this one is actually pushing down on it. Now, what we're going to do is now we got to figure out the angles for this. Now, this particular one is convenient because all the angles are going to come out the same because this it actually has symmetry. If I were to cut it straight down right here at point B, straight down, it mirrors the other side. And so whatever this angle at point A is, it's going to be the same as point C. The angles at point E are going to be the same as point D, and then B is just, they shares the equal angles between the two. So we go in point A and we look. Well, we have a distance of 3, and because I'm cutting it right down at point D, so I'm cutting this member in half imaginarily, and that means it's 3, and it has a rise of 4. So that means that now I know my special triangles, and I know that 3, 4, that means a 5. It's because it's a 3, 4, 5 triangle, and I specifically made it that way. But if you're like, well, I don't believe you, or you don't know your special triangles, then you can just do 3 squared plus 4 squared is 5 squared. So we can actually put it in Pythagorean's theorem. But that's not our angle. That just gives us our distances. But what we can do is figure out our angles. Since I know my adjacent and my opposite, I can use my tangent function. Tangent of my angle is opposite over adjacent. So tangent opposite 3 over 4. And then we have to do the opposite of tangent, which is inverse tangent. So the inverse tangent of opposite over adjacent. So that is going to be the inverse tangent of 4 over 3, which gives me 53.1. Now we can look at point D as well, and we can do the same thing. The tangent inverse is going to be opposite over adjacent. So opposite is going to be 3. The adjacent is 4. And this angle here, and also conveniently over here as well, is going to be the tangent inverse of 3/4 or 36.9. Now, because all the triangles are basically the same here, I'm going to use the angle of 53.1 throughout all the calculations. It's convenient for this particular truss, and I'm picking that truss so that we don't have to deal with the angle and have to do that. When you do this on your own, you will have different angles, so you will need to draw in all your angles here. All right, we will now start at step 1. So this was step 1. Actually, it's not step 1, but it's step A. So we're going to look at point A here, and we're going to draw a free body diagram. So now I'm taking these blue bars now are going to become forces. No longer are they going to be bars. So they're not the lengths. So this is not 6. This is the force AB. And this is the force at AD. So beam AD, what does it feel? That's what our goal is. What is it going to feel? And what's the force of AB? So we have a 10 kilonewton force down, and we have this one pulling over to the right, and we have this one pulling down to the right. So we know that we can actually break this diagonal into its components, into its vector components. So we're going to break it down using our cosine and sine, because the cosine of my angle is my adjacent over my hypotenuse is equal to the 53.1. That's my angle right here. Now, so my cosine of 53.1 is equal to ADX over AD. Now, do not fret and worry about the fact of putting in unknowns. It's okay to put something that you don't know the value yet and just leave it as some unknown value, such as ADX. It's okay. Now I want to move this AD over so it's nice and linear. So AD goes over, and I got AD cosine 53.1 is equal to ADX. I'm going to do the exact same thing for this one, ADY, and I'm going to calculate what is ADY. And I take the sine of the opposite over hypotenuse. The sine of 53.1 is ADY over AD. I'm going to move that AD over, so it's AD sine 53.1. Again, everybody's like, wait, but that doesn't tell me what AD is. You're right, not here, but we're going to use these later on. So now we're going to do the sum of the forces in the y direction. So the y direction, we're going to do this, and we have a y direction here that we know, and we have this y direction, and these two have to equal each other. So the sum of all the forces in the y direction, negative 10,000 kilonewtons, plus ADY has to equal 0. But we know what ADY is. It's right here. AD sine 53.1. So that means that 10,000 has to equal AD sine 53. So we can plug that in. Well, that means I could just divide by sine of 53.1. So I take 10,000 divided by sine of 53.1, and that comes out as AD. So AD is equal to 12,504.9. That is our answer that we want. That's our first answer. And we can actually say that this beam here it holds up 12,504.9 newtons worth of, and because it is positive, it's under compression. Now, let's move over here. The force in the x direction. So we can now find this one. And we can now solve for the AB. So the sum of the forces in the x direction, well, we have AB over here, plus the ADX, which we do know, which is right here, AD cosine 53.1. But wait, we know what AD is, we just solved it right there. So we can plug that number into here, and we can get the 12,504.9 times cosine of 53, and that has to equal AB. So we switch it around, move things around. AB is equal to the negative 12,504.9 cosine 53.1, and that comes out as a negative 7,508.2. So now we have a negative. So notice that this one is going to be a negative 7,000 kilonewton, 7.5 kilonewtons. So this is under tension. Now, let's move on to the next ones. So what we're going to do is that we're going to move to, we did point A, so we're now going to do point D. Point D is not too challenging. It just has one more arrow than point A. But the great thing is we know this one, AD. We already solved it. It was the 12,504.9. I rounded it here. And we know what these are because we already solved for those, the ADX and the ADY. But here's what's wonderful. AD is the same thing as DA. So you can just keep them there. So once we know them, we can just go back to the previous slide and use those numbers. So now what we're going to do is we're going to take and do the exact same things, and we're going to find the the DBX and the DBY for this diagonal. So we're going to break it into its components. So we take again this cosine of my adjacent over my hypotenuse. So the cosine of 53.1 is DBX over DB. Move my DB over, and I get DB cosine 53.1 is equal to the DBX. So that's what that is. Now the sine is just going to be right here, and it's exactly the same thing. We're just doing it again. So that becomes sine of 53.1 is dBy over dB. Move my dB over, and we get dB sine 53.1, which is equal to my dBy. Now we're going to move over and start our sums of our forces, sum of our y's. We're going to take AD. We're going to take the AD sine 53.1. That's our y, the ADY right here, plus my dB sine 53.1, which we don't know the dB yet, and we can plug it in. So that's 10,000 plus my dB sine 53.1 equals 0. We move the 10,000 over. That becomes negative 10,000. And then we're going to move our sine over, divided by sine of 53.1 becomes a negative 10,000 divided by sine 53.1. That becomes a negative 12,540.9. Now notice that this one is the opposite as to AD. AD and BD are almost identical. They're identical in number, but they're opposites in numbers. This is a negative, this is a positive. So this means that this is under compression and this is under tension. All right, so now let's move on to the next one, forces in the X direction. So our sums of our forces are equal 0. So sum of the forces in the X is going to be DE, which we don't know. We have our DX, our DAX, and our DBX. So we know that DE, we don't know what that is. We're trying to solve for that. Minus our this one, which we had in our previous problem for the part A, negative 750.08.2, plus our dB cosine 53. But again, we know dB. We just calculated it. It's right here. So we can plug that in. So we plug it all in and we put it in our equation and we solve for the DE, and DE equals 15,016.4. And because it's a positive number, it's under compression. That means that this one is holding a whole lot more force than compared to these all these other three here. So these three can be a thinner material, but this one needs to be a very thick material, a stronger material, or this bridge will fail. Now we're going to move on to point B. Now point B looks like it's a lot, but it's not hard. It's just a lot of adding. It's literally just adding, a lot of adding. So like everybody looks here and they're going to say freak out. So just follow along and we'll just get through this together. So we're doing the exact same thing. We're breaking our parts down. So we have our AB, which we already know. We don't know our BC. We don't know BE, and we don't know, but we do know our BDX. and our BDY from our previous part in our previous problem. So we know this side, we just don't know this side, which is good because that will help us out figuring out things. So we're going to break them all down. So the cosine of our angle is adjacent over hypotenuse, and the cosine of 53.1 is our BEx over BE. Move our BE over, and we get BE cosine 53.1, which is our BEx here. And then we're going to do the exact same thing over here. I forgot to change that. That's not D. That's not DE. That's BE. So anyways, that should be the BE. I forgot to change that. We'll move on. All right. So now the forces in the Y direction and the up-down directions. We have this one. We have this one, and we have this one. We know this from our previous problem. We know this from what it says, and we don't know what this is. So we can put those in. -5 kilonewtons plus our BDY, which we got from our previous problem, which is -12,504.9 sine of 53.1, plus our BE, which we don't know. Rearrange that equation and solve for BEY, and our BEY is going to be basically rounding up 15,000 even. Now, but that's our BEY. We need the BE. Well, we can then go back down to here and using the sine of functions. BE sine of 53.1 is equal to BEY. So BE sine of 53 is equal to the 15,000. We divide by 53.1, the sine of 53.1, and that gives us our BE, which is 18,757.3. Again, this is positive, so under compression. At any time, if you're feeling a little flustered or trying to figure out things, pause the video and rewind it and kind of just sit and stare at the math. Try to look at the math and see what's happening. All right, now we're going to go to the forces in the x direction. Now the forces in the x direction are going to be this AB. We have this BC, which we don't know, and then we have our BEX and our BDX. So we add those all up, and then so we put our numbers in. So we know our AB, which is 7,508.2. We also know our BDX, which we got over from the previous problem, which is 12,504.9 cosine 53.1. We know our BEX because we just solved for BE, and we can plug that into this one equation. So we know that BEX should just be 18,757.3 cosine 53.1. So we can just plug that in and we get that. So we get a whole string of numbers and realize that all of those numbers right here, and we plugged in everything and we plug all those numbers in. That's a lot of numbers, but realize that's just adding plus, plus, plus cosine 53. That's a multiplying by cosine 53 is equal to BC. So we can add all of those numbers has to equal our BC. So BC comes out as negative 26,278.6 newtons of total force on BC. So that's right here. So that's actually so far the most we've seen that holds up the most. So that even has to be stronger than everything else. And because BC is under tension, it needs to withstand the tensional force being pulled apart rather than being compressed like a lot of these other beams. Now we move on to point E, and we're almost done. This is the last one. So point E, we can actually just do it with one equation because we have only one that we don't know, and that is this EC. So we don't know what EC is. So we're going to do is we're going to do it the X's. So the sum of the forces in the X is EB, ED, which we know, EBX, which we know, and we have ECX, which we don't know. That one's already here. We don't know that one. So we can use that here. We can get the ECX right here, which is EC cosine 3.1, and we can plug those in. So 15,016.4 comes from here. That's my ED. Then we have our 18,757.3 cosine 53. That comes from our EB X. And then we have our unknown. We don't know what that is. So I plug it in, pull my ECX over, and that comes out as 26,278.66. Now that's my ECX. That is not my EC. I have to plug that back down into this equation here, our trig function, and that comes out as EC is equal to ECX over cosine of 53. So I plug that in, our 26,278,000.66. Put that right here, divide that by cosine 53.1, and that comes out as a grand total of 43,767.11 newtons worth of force on that beam. That beam is strong. It has more stress than basically double that and almost triple the rest, and like almost quadruple that beam. So this beam is holding most of the support. That beam is the one we need to look at, make sure it's the strongest beam of this entire system. And because it is a positive number, it is under extreme amount of compression. Now, to double check our work, once we get to point C, we can actually double check it to make sure everything looks good. We can then say, okay, our negative 26.2, we can say that that is our y, has to equal this, and it's x, 43.7 kilonewtons cosine 53, and that should equal this. So BC right here has to equal my 40, this one, our 43.7 kilonewton times the cosine 53 gives us our x component of this, and that has to equal 0, and it does. Negative 35 in my y direction has to equal the component of this in the y direction, so it's this one, and that does equal 0, and everything looks good. So again, this was a longer video, and I understand, and it was a lot of algebra, a lot of trig. I want you guys to rewatch this if you need to. Take copious amount of notes. Write down some questions that you have, parts that you were lost in, and you can ask them in class tomorrow.